Ladies and gentlemen, let's continue with Chapter 8 in the textbook of Heat and Mass Transfer. Chapter 8 is on internal forced convection. We have looked at the differences between internal flow and external flow. Something that's different from internal flow is that in many cases the two boundary layers can meet each other, and therefore it is very important to distinguish between developing flow and fully developed flow. In the laminar flow regime, there are equations that can predict how long it will take. Typically, it is equal to 0.05 multiplied by the Reynolds number multiplied by the diameter. And then we've also done what was called a paragraph laminar or thermal analysis, in which we have looked at the differences in the heat transfer characteristics between a constant heat flux application and a constant wall application. We have also derived some different equations to be used for these two categories. The previous lecture, we've looked at turbulent flow and the many different equations which are available, some which are on the PowerPoint at the moment. We will come back to it a little bit later. And to make the part on the turbulent flow more clear to you, I would like to do a problem, and it is at the back of the chapter, and it is problem 8.72. And this problem says a 10-meter long and 10 millimeter inner diameter pipe made of commercial steel is used to heat a liquid in an industrial process. The liquid enters the pipe with an inlet temperature of 25, a velocity of 0.8 meters per second. A uniform heat flux is maintained by an electrical resistance heater wrapped around the outer surface of the pipe so that the fluid exits at 75 degrees Celsius. Assuming fully developed flow and taking the average fluid properties to be that, determine the required surface heat flux, the surface temperature at the exit, and the pressure loss through the pipe, and the minimum power required to overcome the resistance to flow. So, problem 8.72. Schematically, there is the pipe or the tube. It says that the diameter is 10 millimeters, its length is 10 meters, and it is being heated by an electrical resistance heater, and therefore we've got a constant heat flux heating situation. The inlet temperature is 25 degrees Celsius. The inlet velocity is 0.8 meters per second average, and the outlet temperature is 75 degrees Celsius, and they want us to determine the heat flux as well as, let me see, the surface temperature at the outlet. We're going to indicate it like that, T surface at the outlet, at the exit, as well as the pressure drop and all the pump power. Okay. 10 millimeter diameter tube, 10 meters in length. It is being heated at a constant heat flux. Inlet temperature 25, outlet temperature 75. Determine the required heat flux, the surface temperature there at the outlet, the pressure drop, and the pump requirement. Schematically, we can show the problem like this. Temperature as a function of X. This is the fluid inlet temperature. That is the fluid outlet temperature. So the inlet temperature is going to be 25. The outlet temperature is going to be 75. Okay. Surface temperature, we'll do something like that. Okay. That is Ts, that is the temperature of the fluid, and that would be the separation between fully developed flow, FD fully developed, and developing flow on the left-hand side. Why do I know this is going to be the characteristic? Because it's a constant heat flux. With a constant heat flux, every millimeter that it will flow, it will get the same amount of heat. And therefore, there's a linear increase in the temperature distribution. The properties are given to us as density is 1,000 kilograms per cubic meters. The Cp is 4,000 joules per kilogram degree Celsius. The viscosity is equal to 2 multiplied by 10 to the minus 3 kilograms per meter second. Thermal conductivity K is equal to 0.48 watts per meter Kelvin, and the Prandtl number is 10. If I look at those values, it is close to that of water, but it is not water, it is something different. Right, we've got the inlet temperature, we've got the outlet temperature, we've got the inlet velocity as well as the diameter. So therefore it is very easy to calculate the mass flow rate and the heat transfer rate. The mass flow rate is equal to the density multiplied by the surface area through which it flows, multiplied by the velocity. The density is 1,000. The cross-sectional area through which the fluid flows is pi divided by 4 multiplied by 0.010 square, because it's a 10 millimeter tube, and then the velocity is 0.8 meters per second. So it is quite straightforward to determine the mass flow rate as equal to 0.06 283 kilograms per second. Once we have the mass flow rate, it is now very easy to determine the heat transfer rate. It's equal to the mass flow rate Cp multiplied by the outlet temperature minus the inlet temperature. The mass flow rate Cp multiplied by the delta T between the inlet and outlet. The mass flow rate is equal to 0.06283. The Cp value is 1,000. Outlet temperature is 75. Inlet temperature is 25. So there's a delta T of 50 degrees Celsius. And then the heat transfer rate is equal to 12,566 watts. That's not an engineering answer. That is equal to 12.6 kilowatts. This is the heat transfer rate, but they've asked us to determine the heat flux. So the heat flux is equal to the heat transfer rate divided by the surface area through which the heat transfers. The heat transfer rate is equal to 12,566 divided by the surface area would be pi multiplied by the diameter, which is 10 millimeters, multiplied by the length, which is 10. So the surface area is pi multiplied by the outside diameter, multiplied by the 10 meters in length, and the heat flux is therefore equal then to 40,000 watts per square meter, which is equal to 40 kilowatts per square meter. This is an engineering answer. Okay? Are you all with me? Right? It's important to know the Reynolds number is equal to rho Vd divided by the viscosity. The density is 1,000, the velocity is 0.8, the diameter is 10 millimeters, divided by the viscosity, 2 multiplied by 10 to the minus 3, and it gives us a Reynolds number of 4,000. So, would you say this is laminar flow or turbulent flow? Well, it is one of those difficult ones. If you look at the friction factor or the heat transfer, you'll see that at 2,100 to 2,300, we will have the beginning of transition, but then it does something like that. At 10,000, it is normally always fully developed, so it's going to be in the transitional flow regime, but we can assume the flow is turbulent for the sake of this course. Okay, if the flow is turbulent, and we would like to look at the heat transfer coefficient or the Nusselt number, then we know there is a developing part and there's a fully developed part. But because the flow is turbulent, it will take only 10 diameters before it's fully developed. So it is 10 diameters, is 100 millimeters. 100 millimeters, and this tube length is 10 meters. Therefore, it will, in this first 100 millimeters, it will do something like that. But for the rest of the tube, the flow is fully developed. Therefore, this is a judgment decision, and I think in this case it is a very easy decision, and we're going to say, we're going to ignore the developing part. If we can get the fully developed Nusselt number, then we are very happy. So the Nusselt number, we want the fully developed, we can ignore the developing part. Right, coming back to the lecture of yesterday, where I've given you some of these equations, which are called the first Petikoff equation, the Chilton-Colburn, etc. Which equation should we use? There's lots that you can choose from. As I've mentioned to you yesterday, I'm quite lazy, so I like to use typically this equation because it's very simple. It is called actually the Dittus and Boelter's equation, the Dittus-Boelter equation. I'm going to use this one, Dittus-Boelter. And the Dittus-Boelter says the Nusselt number is equal to 0.023 multiplied by Reynolds to the 0.8 Prandtl to the n. Okay. Where n is equal to 0.3 if you are doing cooling, while n is equal to 0.4 when you're doing the heating of the fluid. And in this case, the fluid is being heated. So n is equal to 0.4 because we are heating the fluid. Right, and now we can go and determine the Nusselt number. It is equal to 0.023 multiplied by the Reynolds number, which is 4,000, to the 0.8 Prandtl number of this fluid is equal to 10 to the 0.4, and that gives us a Nusselt number of 43.99 or 44. Nusselt number of about 44. Again, your question can now be, but what if I used the Glinsky equation or the Chilton-Colburn equation? Well, they're all within 20% from each other. But the Glinsky one is the more accurate one, but as you can see, you have to work much harder to determine it because there are many more. There it is, that equation there. So it takes a little bit longer. You also need to get the friction factor, but it will be more accurate than this equation. So therefore, just to save time, we take the simplest equation. Now that we've got the Nusselt number, we can say the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity K. Nusselt number is 43.99. It's equal to the heat transfer coefficient multiplied by the tube diameter, 10 millimeters, divided by the thermal conductivity, which is equal to 0.48. And that gives us a heat transfer coefficient of 2,112 watts per square meter degree Celsius. The heat flux in general is equal to the heat transfer coefficient multiplied by the surface temperature minus the fluid temperature. In this case, we do not have to work with the log mean temperature difference method because we don't have a surface temperature that remains constant. So it is just actually the delta T. So again, remember, this is just 100 millimeters of 10 meters. So this part is really negligible. So this delta T is constant. Okay. So now that you've got the heat transfer coefficient and the heat flux, you can get this temperature difference. In our case, we would like it at a very specific point. We would like to say we need it here at the outlet. The outlet, we know what is the fluid temperature. So we can write it like that. You see? The heat flux is 40,000. It's equal to the heat transfer coefficient multiplied, the heat transfer coefficient we've already determined, 2,112. The surface temperature at the outlet minus the fluid temperature at the outlet is 75. So from this we can determine the surface temperature at the outlet is equal to 93.9 degrees Celsius. Okay? Right, that was the second part of the problem. The questions were the heat flux, the temperature of the surface here at the outlet, the pressure drop, and the pump power. So let's do the other part. In terms of getting the pressure drop, we have to get the friction factor. Okay, now with the friction factor, where do you get it? Well, from the Moody chart. Moody chart, and there's a Moody chart at the back of your textbook. The Moody chart typically looks like this. The friction factor as a function of Reynolds number. To do something like that. Okay, and this is the friction factor divided by 64. That is for laminar flow. Then there's an area of transition, and then there's turbulent flow. This is for epsilon or d divided, which is epsilon the surface roughness divided by the tube diameter, which is equal to 0. So this is a smooth tube. That's a smooth tube, and then as the tube roughness is increased, we will get different values of epsilon divided by d. Okay, now normally, except if it is specified differently, we will assume it's a smooth tube. And your question would be, is that a good assumption? And the question is yes. Any copper tube or steel tube these days are being made from hard-drawn or soft-drawn tube, and you can go and measure it. They are really, for all practical purposes, smooth. In the old days, when the tubes, which are then called pipes, were casted, they were actually very rough on the inside. But these days, for all practical purposes, you can assume they are smooth. And that's what we're also going to do. So that's now very easy. You can, at a Reynolds number of 4,000, you can go and look what is the friction factor, and the friction factor is going to be 0.0044. That is what I would do. If you're not as lazy as I, you can use the Colebrook equation, and the Colebrook equation looks like this: minus 1 divided by the square root of the friction factor is equal to minus the log of epsilon divided by d divided by 3.7 plus 2.51 divided by the Reynolds number, friction factor F, something like that. You cannot solve it explicitly, you have to solve it iteratively. And if you go and make an assumption of the type of tube being used, you can actually go and refine it up to a friction factor of 0.04425. More accurate, of course, if you do it like that. The best advice I can always give you is, even if you use an accurate equation like this, you get an answer, just go and check it on the Moody chart if it's approximately correct. Very easy to make a finger error. Okay. Right, now we've got the friction factor, then it's easy to get the pressure drop. The pressure drop is equal to the friction factor multiplied by rho v squared divided by 2d multiplied by L. Friction factor is equal to 0.04425. The density is 1,000. The velocity is 0.8. The length is 10 meters divided by 2 times the diameter, 2 times 10 millimeters. And from this, we can determine that the pressure drop is equal to 14,160 pascals. That's not an engineering answer. This is 14.2 kPa, 14.2 kilopascals. Am I going too quickly, or are you with me? Fine? Okay. Got the pressure drop, and now we need the pump power. The pump power is equal to the mass flow rate divided by the density multiplied by delta P. You can go and write it as the volume flow rate multiplied by the pressure drop. And that is equal to the mass flow rate is equal to 0.06 283 multiplied by the pressure drop is 14,160 divided by the density is 1,000, and then that would be equal to 890 watts. So it's about 0.9 kilowatts. This would be with the assumption that the pump has a 100% efficiency. That is never the case. So let's suppose the efficiency is equal to 20% of the pump. Then the pump power would be equal to 890 divided by 0.2. Okay. Ladies and gentlemen, any questions on this problem? Nothing? Okay. So in the textbook there are two more parts which are important before we get to the end of the chapter, and that is Annuli. In many cases, with internal forced convection and heat exchangers, you're going to get to this type of application. What is an annulus? Well, the best way to describe is to look at two tubes, the one on the inside of the other. So there's a tube there, and then there's a tube like that, typically like that. And in many cases, we might have a hot fluid flowing through the annulus and a cold fluid flowing through the inner tube. It can be the other way around, of course. It can also be the other way around. When we get to the chapter on heat exchangers, this will be known as a counterflow heat exchanger. We can also get them in parallel, so that the cold fluid actually flows in the same direction. It is not as efficient, but there are many applications like that. So in this specific chapter, we would like to consider the flow through that area there. So if we draw it like this, what is important now is this area here, the flow going through there, and that area is known as an annulus. It's an annulus, and it is just as important to be able to look at the heat transfer in annulus types of applications. Now, what do we do when we get an annulus? Well, one of the first things that we can do is we can say, well, let's take this annulus and we make use of the hydraulic diameter principle, 4 times the cross-sectional area divided by the wetted perimeter. And then we make of this tube as if it is one like this. So we previously, that is the inner diameter, and that is the outer diameter. And now we've got something different, almost the same, a circular tube, but it has an hydraulic diameter dH. So by using the concept of the hydraulic diameter, we can transform this to a normal tube. And we can make use of the normal equations of Siderin, Tayton, Glinsky, etc. If we go and calculate the hydraulic diameter for an annulus, you've done it in fluid mechanics, 4 times the cross-sectional area divided by the wetted perimeter, then it is equal to 4 times the cross-sectional area through which the flow occurs, is this red area, pi up 4 d0 square minus di square. That is the cross-sectional area, divided by the wetted perimeter. The wetted perimeter will be this area here, plus that area there. So it is pi multiplied by d0 plus di, the outside plus the inside diameter. And the result is that it is equal to the outside diameter minus the inside diameter. Very simple example. If you therefore have an outer tube with a diameter of 40, and here's another tube with a diameter of 30, then that is equivalent to a tube with a diameter of 10 millimeters. Just the difference in the two diameters. And then based on this, we can calculate the Reynolds number, which is equal to rho V multiplied by the hydraulic diameter divided by viscosity. And the same with the Nusselt number is equal to HD divided by K. The heat transfer coefficient multiplied by the diameter divided by K. This is the hydraulic diameter. And to indicate this, you can, in many cases, sometimes they put an H there to indicate it is based on the hydraulic diameter. Now, in your textbook, there's a table 8.4. And this table says it is valid for one surface which is isothermal. What is isothermal? The temperature is constant. And one surface which is adiabatic. What does adiabatic mean? There's no heat transfer on that surface. And the table is given in this format: the diameter ratio, and then they give the Nusselt number on the inside and the Nusselt number on the outside. Typical value, if that ratio is equal to 0.25, then that value is 7.37, and that value is 4.23. And then they give several other values there. They do not give a lot. 0.5 and 5.74 and 4.43. Right. Now, you have to listen carefully. So if you've got now an Analyst, okay, then many students will use these and would say, well, this value is the Nusselt number on the inside, and that value is the Nusselt number on the outside. Okay? This is not correct. Okay? What they mean with that is that this is the inner tube and that is the outer tube. Like that. Okay, so there is the inner diameter and there's the outer diameter. Okay. Nusselt inside is the Nusselt number on that wall there. Okay. And Nusselt outside is the Nusselt number on that wall. You see the difference? Okay. Okay. So this is very limited information. In many cases you would like to have much more. If you would like more information, you can go and look at the work of Dirker and Meyer of 2002 to 2005. Okay. That is Dr. Jaco Dirker. He was my undergraduate student. He did his master's and his PhD, and he did this work where he developed more accurate correlations for flow in an Analyst. And then there were two more students. The one is Van Zyl with Dirker and Meyer of 2013, and then another PhD student named Guma Dixon, Dirker and Meyer, of 2017. It is not that we can't stop with this work, it is just that it is much more complicated than we think, especially if you start looking at different applications of heating and or cooling. Right, any questions on the flow through Annuli? Right. The last part of this chapter is on enhanced tubes. Enhanced tubes. Okay. Now in industry, if we design heat exchangers, again this is the simplest type of heat exchanger, where we've got heat transfer from cold fluid to a hot fluid. Tube in tube, where you just take two circular tubes, you put them the one inside the other, but they take up a lot of area, and for that reason a lot of work has been done to improve heat transfer. How is that done? Well, firstly, if this is the tube, by putting in small grooves on the inside of the tube. My sketch is not so good. The grooves can go through all the way, but then you can also twist them, so, you know, like typically what happens in a rifle tube. They can be twisted. You can put in different fins. Okay. And it can also be done on the outside of the tube. Doesn't always needs to be on the inside, it can also be done on the outside. And then you would of course have tubes which have fins on the outside and they've got fins on the inside. All these different fins has their advantages and disadvantages. And let me see. So here I've Googled quickly, and there you can see some typical sketches of enhanced tubes. Do you see if I go through it? Thousands of different geometries. And of course, if you've got a very complex geometry that you choose, you need to get the information from the manufacturer of the heat transfer coefficient as a function of the Reynolds number, as well as the friction factors as a function of Reynolds number. One of the simplest ways of doing enhanced heat transfer is to take just a piece of flat plate and just twist it like this. You see? Then you put it inside the tube. What would it do? It would of course rotate the flow. It would spiral it, and that would increase the flow path. Makes it longer and would increase the levels of turbulence. Here the same. All of them would do different types of things to the fluid. The other thing that it does, it actually increases the heat transfer area. So it is not uncommon to use enhanced tubes that can decrease your surface area with a factor 2 to 10 times. The advantage of that, of course, is that your heat exchanger becomes 10 times smaller, and or you can do the other opposite, and that is to keep the area and the length the same, do enhanced heat transfer and increase the efficiency of your heat exchanger. And of course, then the third option is to do a compromise between the two of increasing efficiency and or decreasing the surface area, the cost normally, and also the size of your heat exchanger. If you would like specifically to look at twisted tapes, you can go and look at the work of Burgels, Art Burgels, and then also the work of Meyer and Abolurin. 2018, published recently. You can go and get all that heat transfer coefficients in those articles. Right, I want to do an example, but I see I'm not going to be able to finish it. Are there any questions? If not, then ladies and gentlemen, thank you very much, and then I'll see you again next week. Thanks.